periodic complex, exponential, and sinusoidal signals. A second important class of complex exponentials is attained by constraining a to be purely imaginary. Specifically, consider x of t equal to e power j omega naught t. That is, that exponential, complex exponential is attained purely imaginary. Purely imaginary. That is, x of t equal to e power j omega naught t. Here. An important property of the signal is that it is periodic. Important property of the signal is that periodic. To verify this, we recall from equation 1.1 that x of t will periodic with period t if e power j omega naught t equal to e power j omega naught same up to here, this one, then plus add t, that is period. Okay. Then or since e power j omega naught of t plus t equal to, that is this is okay, equal to e power j omega naught t, that is in power here multiply. Which one is power? Here multiply will come. Mathematical tools. So for this portion got here, and then for this portion got here e power j omega naught caps t here, that is uppercase, here t, here lowercase t. It follows that for periodicity we must have e power j omega naught t equal to 1. It follows for that for periodicity, is to we must have e power j omega naught t, e power j omega naught t equal to be 1. It follows periodicity, we must have this one equal to 1. If omega naught equal to 0, this one omega naught equal to 0, then x of t equal to 1. Then x of t equal to 1. Okay. That is, if omega naught equal to 0, then x of t equal to 1, which is periodic for any value of t. T uppercase t here or full period t or periodic, which is periodic for any value of t. Any value of t. If omega naught equal to 0, not equal to 0, then here 0, omega naught equal to 0, then x of t equal to 1. If it is not 0, then what will happen? Then the function, then the fundamental period t naught of x of t naught, that is period of x of t, denotes that is smallest positive value of t, that is smallest positive value of t, for which equation 1.23, equation 1.23, okay, hold is here, that is t naught, fundamental period t naught equal to 2 pi divided by mod omega naught. If omega not equal to 0, then x of t equal to 1. If omega not equal to 0, then the fundamental period of x of t, that is smallest polynomial of t for which equation hold is here, if not equal to 0, then 2 pi divided by mod omega naught. Thus, the signals e power j omega naught t and e power j omega naught t minus e power minus j omega naught t. This is negative exponential. This is positive side exponential. Have the same fundamental period. Have the same fundamental period. That is same. For this one also same. For that is in negative exponential also, for negative exponential e power minus j omega naught t equal for this purpose period same only, t naught equal to 2 by divided by mod of omega naught mod. Here in positive side positive exponential e power j omega naught t fundamental period also same, this one only, t not equal to caps t not uppercase t not equal to 2 by divided by mod omega naught. Thus the signals e power j omega naught t and e power minus j omega naught t have same fundamental period. For same fundamental period. A signal closely related to periodic complex. A signal closely related to periodic complex exponential is the sinusoidal signal. A signal closely related to periodic complex. Periodic, repeated. We can say repeated, that's a signal. Complex exponential, with the complex exponential is the sinusoidal signal. X of t equal to a cos of omega naught t plus pi. This is the sinusoidal signal. As illustrated in figure 1.2g, continuous time sinusoidal signal. Here cos pi, a cos pi, a amplitude is totally x of t equal to a cos of omega naught t plus pi. This is amplitude, total amplitude. Here cos pi, that is in x-axis, sorry, in y-axis, while t equal to 0, the cutting point a cos pi. From top upper maximum amplitude from 1, here starting, here ending. This is equal to t naught, fundamental period. This is 2 equal to t naught equal to 2 by divided by omega naught. This is time t. So as illustrated in figure 1.20 with the seconds as the units of t, the units of pi and omega are radians. For this one, for this time t seconds, for pi and omega naught, both are radians only. That is for pi radians and omega naught t radians per second. Radians per second. So how much time? That's why here multiplying the time respectively. It is also common to write the omega naught equal to. It is also common. It is also common to write omega naught equal to 2 pi f naught. 2 pi f naught. 2 pi f naught. Okay, that is this here omega naught. where f naught has the units of cycles per second or hertz, where f naught has units of cycle per second or hertz. Like the complex exponential signal, the sinusoidal signal is periodic with the fundamental period t naught given by equation. Like the complex exponential signal, the sinusoidal signal is periodic with uh, periodic. This one is periodic only. Sinusoidal signal, best example for periodic signal. Same repetition. Where finish then same. Okay. Here then repetition same. Okay. Like the complex exponential signal, the sinusoidal signal is periodic with the fundamental period t naught with the fundamental from top to this top. Okay, in amplitude in this sinusoidal. So this distance is t naught. Okay. That is fundamental period. Okay. Then uh, fundamental period equation this one. T naught equal to 2 by divided by mod omega naught. So sinusoidal and complex exponential signals are also used to describe the characteristics of many physical processes, in particular physical systems in which energy is conserved. For example, as shown in problem 2.61, the natural response of Ln of an LC circuit is sinusoidal, as is the simple harmonic motion of a mechanical system consisting of a mass connected by a spring to a stationary support. The acoustic pressure variations corresponding to a single musical tone are also sinusoidal. Okay, that is what we have seen in problem 2.61. That one same here in this LC circuit. Sinusoidal as is the simple harmonic motion of a mechanical system consisting of a mass connected spring to a stationary support. So where is the vibration? We can say that one also. Example generally, we can say sinusoidal signal. The acoustic pressure variations corresponding to a single musical tone are also sinusoidal signal. Acoustic pressure vibrations corresponding to a single music tone, only one music tone, also sinusoidal signal. Example for that. Then by using Euler's relations, the complex exponential in equation 1.21 x of t equal to e power j omega naught t to 1 can be written in terms of sinusoidal signals with the same fundamental period e power j omega naught t equal to cos omega naught t plus j sin omega naught t. We can say this one for even signals, this one for odd, imaginary, you can say. Okay, e power j omega naught t equal to this formula. Okay, cos theta plus I sin theta like this. E power theta equal to. So here e power j omega naught t equal to cos omega naught t plus j sin omega naught t. So E means two combination is there, cos plus sin. Cos in even part like this, j sin in imaginary part. Add for j purpose, j also for imaginary part mentioning only. So similarly, the sinusoidal signal of equation 1.2